For the next 20-25 minutes or so, let's really focus on effect sizes in order to find out our way to quantifying our effects, to interpreting our effect sizes, and to comparing and converting them. And we'll also explore how strong are typical effects in psychology. But first, what is effect size? An effect size is basically the size of the association or difference that we are interested in. In order to get closer to this issue, imagine this research situation. Imagine that you are studying the difference in examination scores in two groups of children. One group who have received extra tutoring out of school, and another group who only attended the regular lessons at school. So now imagine two different researchers who might want to do this in two different ways. One researcher is saying, I will just calculate the correlation between tutoring and examination score. And even though tutoring is a binary variable, it's completely fine to do it. This correlation will be called point by serial correlation. It will be mathematically the same as Pearson correlation. Or if the tutoring is measured on some interval scale in terms of the number of hours, for example, this will be just your good old Pearson correlation. And in the case of Pearson correlation, we know that it's the R itself which expresses the effect size. The larger is R, the larger is our association. The stronger is our association. There is, however, another more tricky situation. Another researcher says, and I will just take two groups of children, a group of children who received extra tutoring and a group of children who did not. And for each of those groups, I will calculate mean and standard deviation, and then I will try to quantify how different are the means in those two groups. What's not so intuitive is that these two researchers are actually testing exactly the same hypothesis, and it's just the parameterization of the data that they are using is different. But the effect that they are exploring is the same, albeit with two different statistical methods. But before we try to compare the results of their findings, let's first find out how can we quantify the size of the effect, the size of the difference between the means in the second case. If you have two groups whose mean scores you are trying to compare, the magnitude of these group differences can be expressed by a simple statistic which is called Cohen's d, after Jacob Cohen. Jacob Cohen, a very interesting author who wrote probably the best textbook on regression. If you're interested in regression, I totally recommend Cohen, West, and Aiken. And he proposed a whole bunch of different effect size indicators, but Cohen's d emerged as the most popular. It is simply the difference between two means expressed in standard deviation units. So in a sense, it is standardized. Because expressing it in raw scores would have made no sense. It would be dependent on the scale. But if we express the difference between the means and standard deviation units, it's kind of similar to z-scores. We standardize this difference. How do we calculate Cohen's d? Basically, it's the difference between two means, x mean 1 minus x mean 2, divided by pooled standard deviation. What is pooled standard deviation? Well, there is this scary formula where the standard deviation for each of the groups is weighted by the size of this group. So if one group has 1,000 participants and another group you're comparing with has only 100, these groups are different by an order of magnitude. Obviously, it would make sense that the larger group would contribute more to the estimate of your standard deviation than the smaller group, where the estimate is less precise. That's the reason why this formula is used. However, if your groups are equal in size or are very similar in size, you can simply use here in the denominator just average standard deviation across those two groups. So you calculate standard deviation for group 1, for group 2, and you average the results and you get average standard deviation. Some online calculators also use this formula. And graphically, you can see that the larger is Cohen's d, the more these two distributions diverge, and the less overlap there is between them. Now, when Cohen introduced the concept of his Cohen's d, he proposed some tentative guidelines to interpret the size of this difference between the means. Basically, it was based on completely intuition. He said, okay, if Cohen's d is 0.20 or smaller, let's call it small. If it's about 0.50, let's call it kind of medium. And if it's above 0.80, let's call it large. But this was completely arbitrary. It was not based on any substantive analysis of research findings. And Cohen, of course, was aware of these limitations. But there is also another measure of effect size, Pearson R. And Cohen also proposed some guidelines to interpret the size of the correlation. He said, if correlation is 0.10, let's call it small. If it's about 0.30, let's call it medium. And if it's about 0.50, let's call it large. But then again, these guidelines, there is some substance to them, but they don't really correspond to real sizes of effects. And also, the question is whether these two estimates of effect size are same or different. Do these values correspond to one another? So if two different researchers use two different measures of effect size, would these interpretation guidelines correspond? To answer this question, I simply simulated this kind of study in R with two groups. Let's call them group 0 and group 1. So at the bottom you see graphs of 3 point biserial correlations. And at the top you see graphs of exactly the same data in the form of overlapping distributions, as you would graph the difference between two means. And here I have calculated the values of d that correspond to these three values of r, 0.10, 0.30, and 0.50. And you can see that r.10 does really correspond to d of 0.20, in line with Cohen's interpretation. However, an r of 0.30 corresponds to a difference of 0.63 standard deviations between the means. So d is a bit larger than Cohen would expect for a medium effect. And for a correlation of 0.50, it corresponds actually to a very strong d of 1.15. So this correlation coefficient, it does not intuitively appear as strong, but in fact, it's a much stronger effect than you would expect. So how can we actually compare R and D? Obviously, R goes from -1 to 1, so there is a limit. D goes from 0 to theoretically infinity, because the difference between two means can be 2, 3, 4, 5, 6, even 10 standard deviations, and so on, if your groups are extremely different, if they come from two different worlds like Mars and Venus. And here, to blow your mind up a little bit, I have prepared this table where for each value of correlation coefficient r from 0 to 1, I have calculated a corresponding value of Cohen's d. That is, if there were two groups, what would be the difference in standard deviations between those two groups? And I have also calculated a third measure of effect size, also very common in psychology, which is called R squared, or eta squared in the context of ANOVA. It's the same. It's the percentage of the variance of one variable explained by the other variable, or the proportion of common variance of two variables. And R squared is basically the square of R, of correlation coefficient. So it's also called coefficient of determination, R squared. Yeah. So these are the three indicators of effects that are commonly used in psychology, and now we know that we can express the same effect in either of them. The question is, which one of them is more advantageous to express your effect in? There have been special studies when researchers took the same effects, expressed them in different units, and gave them to other researchers who were kind of acting as reviewers, and were asked to judge the practical importance of these effects. And these researchers found that the worst case is presenting your effects in terms of R². If you say, my effect explains 4% of variance, the reviewers will say, meh, not so strong. Is it really important? But then you can instead express it in R, and you can say the correlation is 0.20, and then reviewers will say, oh, okay, well, maybe that's not too bad. And if you express it in Cohen's d of 0.41, this is kind of the best situation, because a difference of 0.4 standard deviations, psychologically it's kind of larger, even though it's the same result, but the number is larger, so it appears intuitively to be a stronger effect, which is of course not the case. But still, there is this bias. So when you choose how to present your effects, you can choose between probably R and D, but then R is more universal. So nowadays, I think there is not so much bias associated with R, because people have used the real effect size in psychology. However, another problem appears when you need to present your effect to people who are not specialists, to people who are not psychologists. And if you start telling them something about correlation, they will say, I'm not sure what it is, or what a standard deviation is, they might not even know. And even if they know, they might not be convinced by these numbers. So you need to find a way to explain your effect to them in a way that would be much more intuitively appealing. And some people have come up with different ways to do it. So here you can see 3 different alternative effect size estimates that you can use to explain your effects to non-specialists, to lay people. The first is called common language effect size. It is an effect size indicator for the situation of comparison between 2 groups. Common language effect size is interpreted as a chance that if you take a random person from one group and a random person from another group, that a random person from one group will have a higher score. So, for example, you're comparing children who received and did not receive extra tutoring on the resulting United States exam score, ЕГЭ. And you see that the correlation between tutoring and ЕГЭ score is, for example, 0.30. But this is not so convincing. Instead, you may say a child who has received tutoring in 2/3 of cases will be more successful at ЕГЭ than a child who did not receive extra tutoring. And this is much more intuitive as an interpretation. However, this interpretation is only good for the case when you have 2 genuine groups. In case if both of your variables are interval variables, there is another thing which is called common language effect size for correlation. And it's basically an adaptation of common language effect size for correlations. If you have 2 correlated variables, what are the chances for a pair of people chosen randomly from the sample, if one person has a higher score on one variable, that he or she will also have the higher score on another variable? The formula for CLR is not complicated, but you can simply use the table. And I used this table when I interpreted the findings of our study when we used artificial intelligence to predict people's personality traits from their photographs. And then we investigated the correlation between predictions of personality traits made by artificial intelligence, by neural networks, with actual questionnaire scores that people have produced. And we found that on average, across 5 traits and across 2 genders, this correlation was 0.23. And in order to interpret it, we used this CLR measure. So in order to look up CLR, you need to find a row where there is the first digit, 0.20, and then a column where there is the second digit. So a correlation of 0.23 corresponds to a CLR of 0.574, which means that if a person was rated by artificial intelligence as having a higher score on a personality variable, there is a 57.4% probability that that person also has a higher score on self-report questionnaire. Now, this might not be as true, might not be as impressive. CLR is always smaller than common language effect size, but because for CLR there are no distinct groups. People are drawn from the same distribution. As a result, they are not necessarily very different. And finally, there is a third indicator of effect in everyday language proposed by Robert Rosenthal, the same guy who described Pygmalion or Rosenthal effect. And it's called binomial effect size display. Robert Rosenthal proposes to interpret R in case if both variables are dichotomous, truly dichotomous, and in case if R is a tetrachoric correlation, he proposed to interpret it as difference in outcome rate between 2 groups. So imagine that people are split equally into a group where they are treated and a group where they are not treated, and imagine that in the end half of them end up alive and half of them end up dead. Scary experiment, but it's just a thought experiment. So then this tetrachoric correlation of 0.32 will be equivalent to the difference in outcome rates of 0.66 versus 0.34 in the 2 groups. So in the group of individuals who were treated, the chance of being alive will be 0.66, and in the group of individuals who were not treated, the chance of being alive will only be 0.34. And this difference between 0.66 and 0.34 is actually this correlation, 0.32. So this presentation is much more intuitive, but of course it assumes that outcomes are distributed equally, which is sometimes not the case. So if the percentage of people who are dead is very, very small relative to the percentage of people who are alive, there will be some asymmetry, and this binomial effect size illustration will not be very intuitive. So in order to kind of make those effects more tangible, let's take a funny example, which I discovered in one TV show called Lie to Me, where there was a Dr. Lightman, played by Tim Roth, who was a psychologist, and in that show they were mentioning a lot of interesting scientific findings. So because I was interested in this face perception issue and in those studies, there was one finding that they mentioned there, that people are actually able to accurately distinguish straight men from gay men based on facial image alone. And in the TV show they said, oh, people can reliably distinguish. So I looked up this original paper, and I looked up the effect size. And they conducted, I think, 3 different experiments. And an average effect size across those experiments was R of 0.32. Kind of average correlation. So if we interpret R squared, we can say that the actual sexual orientation of a male subject only explains 10% of the variance in how gay or straight that person looks. However, for a common language effect size, imagine that you have a random pair of guys like here, Freud and Tchaikovsky, or Patrick Stewart and Ian McKellen. One of them is always gay and another one is straight. So common language effect size indicates that for such random pairs, in about 2/3 of cases, in 68% of situations, the guy who is really gay is going to look more gay, but in the remaining 1/3 of the situations, the guy who is really gay will look more straight. So you can not really be confident when you make those judgments. And a common language estimate of R. So imagine that you take a random pair of guys who have unknown sexual orientation. So if you see that one is looking more gay, the chance that that person is really more likely to be gay is about 60% only. So in about there is a fairly high chance of you being mistaken. Now, of course, in the TV show, they kind of claimed that this effect is strong enough for practical use, but in practice, you can see that it's not as strong as they claim it to be. And you need to have these interpretations of effect size to put it into right context. However, if you are disappointed in people's ability to tell gay people from straight people, remember that this effect only concerns the face, and it does not concern hairstyle or behavior or clothing, etc. Maybe those additional cues contribute to prediction. So altogether, maybe the prediction quality is higher. But I hope you get the idea. So why did I even take this effect? It's not because this topic is very special, but just because, interestingly enough, this effect of people's ability to tell between straight and gay men corresponds exactly numerically to another very classical effect size discovered long ago in the classical study of Smith and Glass, when they investigated the efficacy of psychotherapy. And they found that across different treatments, across different outcomes, across different designs of studies, the average effect of psychotherapy, or the average correlation between being in psychotherapy for a problem and some outcome variables, was 0.32. And if you look at this correlation, if you are not a psychologist, you might think, just 0.32? Such a small correlation. People in physics will think, oh, it's nothing, absolutely. Should we even pay those psychotherapists? Now, if you want to convince people to pay psychotherapists their money, you probably need to find a way to explain this effect to them. So we can use common language effect size. And we can say, let's take a random person who is in therapy and a random person who is not in therapy but has the same problem. So there is a 68% chance that a person who's in therapy is feeling better. Is it worth paying your money for psychotherapy? Probably yes. But if they are not convinced, you can use binomial effect size display. And you can say, if we take a person who is in therapy and who is not in therapy, the chance of getting cured if you're in therapy is about 66%, and the chance of getting cured if you are not in therapy is only about 32%. So this is a very tangible difference between outcome rates. However, binomial effect size display kind of assumes that there is an equal number of people who are cured and not cured, and who are in therapy and not in therapy. So in this ideal world, this would be the difference in the outcome rates. In real life, it's slightly different, but it's a convincing illustration, I hope. And if we look at real effect size in psychology, one of the best sources I found was this meta-analysis of 380 meta-analytic studies. So it's a meta-analysis where people have combined basically all the effects found in psychology and tried to find out how many effects of different sizes there are. So overall, they discovered that about 1/3 of effects are below 0.20, about 1/3 of effects are above 0.30, and the middle third of effects are 0.20 to 0.30. If you're evaluating some psychological assessment, it's slightly stronger. If you're evaluating some psychological treatment like psychotherapy, it's slightly weaker. So Smith and Glass's meta-analysis producing 0.32 produced an effect somewhere in the upper third. Maybe it was biased up, or maybe later studies of treatments included some treatments that were not so efficacious. Nevertheless, if you're getting a correlation of 0.25, it's not a reason to be disappointed. It's a kind of average effect size for psychology. And in some areas of psychology, the picture is different. For example, in social psychology, it's slightly stronger, but if you take psychology of individual differences, where the outcomes are usually objective, the median effect size is 0.19. So correlations are really fairly weak. And another conclusion is that you need to plan for a correlation of about 0.20 if you want not to miss a typical effect size in psychology. And if you're doing a power analysis, you're playing your sample size. So I would definitely plan for a correlation of around 0.20 at least. And of course, even weaker effect sizes can be quite practically important. This classical example comes from a book by Robert Rosenthal, and it's the effect of taking small doses of aspirin to prevent heart attacks. Basically, it's the correlation between taking versus not taking aspirin and the outcome, having or not having a heart attack during a subsequent period for people who are already at risk for heart attacks. And here you can see that this tetrachoric correlation coefficient is 0.034. It's very, very small. It's not significance level. It's the actual correlation itself. But if we look at the binomial effect size display, imagine that 1,000 people who are at risk for a heart attack are taking aspirin. As a result, 34 of them will avoid heart attack just thanks to aspirin. So if aspirin is harmless, maybe it's a recommendation that is worth making to everyone, because 34 people out of 1,000 can be saved from heart attack. And if 1 million people are doing this, obviously the number of people who are going to be saved and the number of money that the healthcare system will save will be quite substantial. So this correlation has a huge practical significance, and that's why doctors advise to patients to take small doses of aspirin every day. However, this correlation is very, very weak. If you want to discover it, the minimum sample size at which it even barely becomes significant at p less than 0.05 level is about 3,000 individuals. So imagine that you want to discover this correlation in your study. You have a hospital, but maybe to collect this number of patients, you need years and years and years. And if you want to have good statistical power to test this hypothesis, imagine that some foundation gave you $1 million to investigate the effect of aspirin. And you say, okay, I want a statistical power of 0.95. And the number of patients that you need to recruit is over 10,000. So basically, it's impossible to conduct such a study in a single sample, in a single place. The only way to get this kind of data is to combine data from different studies, from different places, to perform some kind of meta-analytic combination. And it's thanks to meta-analysis that this finding was available. So even a very small effect size can be of huge practical importance. Now, to conclude our discussion of effect sizes, just to mention quickly another effect size that you might sometimes encounter is called odds ratio. Odds ratio is used in medicine and used in health research, where people have binomial predictors and binomial outcomes, treated, untreated, alive, dead, and so on. So what is odds ratio? It's very simple. You calculate odds of being alive if treated, and this is basically the number of people who are treated and alive divided by the number of people who are treated and now dead. And you get your odds of being alive if treated are 1.94 to 1. And your odds of being alive if untreated are vice versa, also divided 0.52. And then odds ratio is the ratio between odds of being alive if treated divided by untreated. And it's 3.73. So in your research report, you write a person is 3.73 times more likely to be alive if treated as opposed to untreated. And this is very convincing. That's why it's very often used in health research, but it only makes sense to use it in a case of binary predictors and binary outcomes. Obviously, in psychology, it's rarely that we have variables measured on such a low scale. Usually, at least one of the variables is interval, and then we use common language effect size or D or R, etc. But just if you encounter odds ratio, don't be scared. It's nothing complicated. So to conclude a little bit our discussion of effect sizes, in psychology we typically use R, coins D, and R squared or eta squared. What you need to remember is first of all how they compare. And a very important thing is that any general interpretation of a correlation as strong or weak makes no sense at all out of context of a specific research field. In different research fields, the same correlation can be strong in one field and weak in another one. So it's best not to interpret your correlations as weak or strong if you don't, if you're not very clear about your context and about the previous findings that you're comparing it to. And what's important is we need to know how can we explain our sizes to lay people and to policymakers in order to convince them that a correlation of 0.32 is a huge reason to pay your money to psychotherapists, because psychotherapists will help you. So this was a little introduction into effect sizes.